Today's event is a testament to the power of collaboration, determination, and achievement in our shared mission to cure cancer. From NFCR, all of you here in this room, to people around the globe, we have demonstrated our collective passion, persistence, and commitment to helping cancer patients in the US and around the world. We have momentum in our movement. We must keep it going. So to kick off tonight's program, I am honored to present a trailblazing physician scientist, renowned author, and a Pulitzer Prize winner, Dr. Siddhartha Mukherjee. Dr. Asra Raza, who is a long-term collaborator with Dr. Mukherjee, another esteemed physician scientist and best author, was supposed to be here, and she wanted to be here so much, but she had a last-minute emergency. So I end up doing the job of introducing Sid. So Sid, I won't be as poetic as Ezra, but you're gonna have to put up with me. Dr. Mukherjee is one of those people you want to have, and you want to have it for dinner party and get to know in your journey of life. He has many talents. A Rhodes Scholar, a scientist, an oncologist, and founders of more than a dozen of biotech oncology companies. And as I said earlier, the Pulitzer Prize winner author. Probably everyone in this room have read his best book, most famous book, The Emperor of All Maladies. If you haven't read, get a copy. Actually, we have some copies Dr. Mukherjee will sign for you. And Dr. Mukherjee has other famous books, The Sound of Cell and Genes. Those are also award-winning books. And he writes for the New York Times Magazine and the New Yorker, one of my favorite magazines. And he is a native from India, and Dr. Mukherjee received, get ready to hear this. Dr. Mukherjee received his bachelor degree from Stanford University and was a Rhodes Scholar, as I mentioned, from the University of Oxford, and had 2 residence at Harvard Medical School. Actually got to the medical school degree from Harvard Medical School and had a residency at MGH and then Dana-Farber. And now he is an associate professor at the University of Columbia. Which school you haven't been to? Looks like he probably doesn't need a sleep. The best of all, he's NFCR's one of the teams, collaborating teams, working on early detection and early intervention. So let me present you Dr. Mukherjee.
It's an immense pleasure to be here. I am among friends, and I'm among old colleagues, people I've known for not 5 years, not 10 years, but 20 years. And it's really quite amazing to see how our field is evolving and continues to evolve towards prevention, treatment, and cure. I want to talk a little bit today about what I think about visions of a medical future in cancer. This is going to be a very broad-ranging talk. I will occasionally ask people to stand up because I think it's very important to recognize in this audience people who are fundamentally important in our ecosystem and in the ecosystem of finding cures for patients with cancer. So when I ask you to stand up, please do so. Don't be hesitant because you need the applause that is deserved to you. When my first book was published, there was a beautiful review by Stephen Shapin, a great historian of science, who wrote that a world in which cancer is normalized as a manageable chronic condition would be a wonderful thing, but a risk factor world in which we all think of ourselves as precancerous would not. This is a very complex statement, and I've thought about it a lot, because it means that all of us, as we age, become, in some ways, precancerous. And therefore, a world in which the worried well, as someone has put it, is constantly thinking about what the next frontier of cancer for them is a world that we don't want to live in. How do we avoid that world? We avoid that world by providing real medicines and real preventative mechanisms for people who enter the precancerous universe. Because then they're not worried. They may not be well, but they're not worried about not being well. We find mechanisms to remove them away or to take away from them the anxiety of cancer. And if there's one thing that connects my speech today, it is about what we can do to remove the anxiety of cancer, psychologically, socially, culturally, spiritually, and of course, medically. And Stephen Shapin continued, that world might decrease the incidence of some forms of malignancy while hugely increasing the numbers of healthy people under medical treatment. And it would be a strange victory indeed, in which the price to be paid for checking the spread of cancer through the body is its uncontrolled spread through our culture. I really want us to think about that last line, because as we move more and more towards a world in which we remove cancer from our bodies, we move towards a world, and I really strongly believe in cancer prevention and early detection, a world in which this uncontrolled spread through our culture becomes important. And so we need new mechanisms and new ways of thinking about cancer where we do not think about it so much as a deadly end to our lives, but as a normal process of aging and a process by which that can be controlled, caught, and hopefully eliminated from our lives before it takes control of everything that we do. And so at the highest level, I want to tell you about a few major points. Number one is that we are beginning to understand cancer at a cellular and molecular level. There's no doubt about that. There are people in this audience, again, I'll ask you to stand at the right moment. When we understand cancer at the cellular and molecular level, that understanding has highlighted certain things. Number one, that there's an enormous diversity of cancer at individual levels. This is not something to be scared of. This is something to embrace, to understand. It is a fact of life. It is a fact of cancer. And that as we move along to the enormous diversity of cancer at individual levels, we need to devise individual treatments. This diversity may demand precision medicines or partially individualized therapies. There are two caveats to this statement. I said may demand and partially individualized therapies. And by that I mean that there are some commonalities in cancer that we're using to develop therapies, and there are some distinctive aspects. So, in other words, a woman with breast cancer may share many features that are common with another woman with breast cancer. And she may also have some things that are unique to her. And finding those distinctions and differences is the wisdom of medical science. You may realize that this, what I'm talking about, is the wisdom of human beings, finding our distinctive characteristics and finding how we differ from each other is the wisdom of life. And so, cancer, in fact, is giving us a reflection of the wisdom of our own lives, that we are together regardless of where we come from, but we are also separate and individual because we have distinctive features. And that's an important piece of wisdom that cancer is teaching us, even if we don't like it. It is the reality of what our lives are. Secondly, we are increasingly aware of the idea that early treatments are likely to bring benefits. And so, somewhat in synthesis, if we could detect early and treat precisely, the 2 points I made before, we are likely to be themes in the medical future of cancer. The one thing to be careful about, and I always warn about people, that as we detect early and treat early, and as we treat precisely, we enter a world of surveillance, diagnosis, and treatment that carries cultural burdens that we are yet unprepared to make. And I will rely on people who are not doctors here. They may be doctors, but who are not only doctors here, people who are in the journalistic profession, people who are legal scholars, people who are scholars of medicine, people who are scholars of anthropology, to remind us that this is a world that we are totally unprepared for, and to prepare us for this world. And we need help from you too. I'll start with a little bit of history because history is interesting to me. This is the first document that we ever know that is a history of cancer. This is the Edwin Smith Papyrus. It happens to be one of the oldest human documents of cancer. And it talks about a mass in the breast as dense as a hemat fruit. In this hieroglyph, there is also a very dismal statement that there is no treatment. That's not true today. It is not true that there is no treatment today. There is treatment. But this is from 4,000 years ago. And it's a reminder that cancer is not a disease of modern times. It's a disease of ancient times. And it is just that we have begun to detect it. We have begun to understand it in ways that we hadn't done either before. People often ask me where the word cancer comes from. It was Galen who used the word cancer as the metaphor of the crab. No one exactly knows why. Some people think that it was a cancer buried under the skin that looked like a crab buried under sand. Some people think that it has to do with the pain that's caused by cancer. But nonetheless, Galen used the word of the metaphor of the crab, karkinos, and that metaphor stuck. We are still using that metaphor for cancer, often without knowing why, and often without knowing exactly what we convey to patients when we use the word cancer. Often patients will ask me, what's the word cancer mean? And I tell them the entire history. I tell them the meaning, the future meaning, and I tell them that it's not something to worry about, because that meaning changes just like all meanings in words change over life. We move on to Virchow many years later. And Virchow was the first person to understand cancer as the betrayal of the self. These are the words that he used. Virchow was a great scientist. I've profiled him in 2 of my books. Virchow had many roles in life, but perhaps one of the most important roles was that he was the first person to begin to think about cell biology. He was a cell biologist at heart long before he was a cancer biologist. In fact, he was not even recognized as a cancer biologist. But Virchow began to think about the idea that cells came from all cells. There were lots of theories before Virchow about how cells arose. People thought they arose from uh, uh, phenomenological things. Um, they came about as accretions of crystals. But Virchow said cells only arose from prior cells. Omnis cellula et cellula. Very important phrase in Virchow's writings. Now, if that's true, then the consequence is also true, which is that if all cells come from cells and only from other cells, if cells can only give birth to cells, then it must be true that a cancer cell came from a normal cell. Think about that for a second. That means that something must have happened to a normal cell. Some process must have happened to a normal cell to transform it into a cell that no longer obeys the laws, the boundaries of normal cell division, and thereby causes cancer. That process eventually began to be known as transformation. Transformation because a cell had now transformed itself into a cell that was no longer able to carry out its normal cell division and invade, in a malignant way, invade tissues and cause cancer. So in some ways, even without knowing it, that simple statement of the arise of cells from normal cells created the entire field of oncology. I want to point this out because I think there are many basic researchers in this audience. And many of these basic researchers make statements about cell biology, genetics, etc. It's very important for many of these basic researchers to understand that what you do in life, what you understand in life, may have nothing to do with cancer, but will eventually almost always impact cancer. And that is because cancer is a disruption of the basic biology of normal cells. So, this is the first standout call. If you happen to work on the basic biology, cell biology, biochemistry of cells, stand up, please, because I'd like to recognize you. And if no one applauds, I will applaud. Stand up. Thank you. And I'd like to add that Albert Szent-Györgyi was not a cancer biologist. He made many discoveries in metabolism, in vitamins, in mitochondrial development, etc. But in every single way, that's one way that you recognize the fact that if you're working on the basic science of cells, you are a cancer biologist, whether you like it or whether you don't. All right. The first attempts then to extricate cancer out of cells was surgical. And so why not? It makes total sense. If you have a malignant cell, that cell is spreading, why not take it out? Why not cut it out? This is William Stewart Halsted performing his famous Halsted mastectomy. The Halsted mastectomy has a very complicated history. It was a theory that was very correct and very wrong. Very correct in the sense that Halsted understood that in order to cure cancer, you'd have to take the cancer out of the body. Very wrong in the sense that Halsted thought that the more cancer you took out of the body at one particular time, the more likely you were supposed to cure cancer. There's a long history of this in my book. I won't go into it in great detail. But just to remind you that Halsted was a very important figure in all of this. He was also a cocaine addict. But all of this said, Halsted was very seminal in understanding how and why you can use surgical therapy, and I would say, and as an extension, radiological therapy to cure cancer. And he was the first person to understand that cancer begins as a local disease, one cell transformed, becoming malignant, and ultimately spreads into a systemic disease. So, if you happen to be a surgeon, regardless of what discipline of surgery you're in, can I please ask you to stand? Thank you. All right. And then in the 1950s, people began to recognize that just removing a local cancer would not be sufficient. And what other example to use than a cancer where there is no local therapy, but blood cancers? Blood is present throughout the body. Blood moves throughout the body. And so this is the beginning of what we now call chemotherapy, chemical therapy, in which you send a chemical through the whole body and try to create, kill the cells that are dividing. This is a picture of Robert and Elliot Sandler. And I'm going to tell you a nice story about this. I was writing my first book, and I'm very interested in writing books as a series of stories. I don't believe in writing didactic books. And so I was in search of the first patient, the first child who received chemotherapy for acute lymphoblastic leukemia. We'll come back to this picture in my later slides. And I came up to a dead end. I looked and looked and looked through libraries. I spent hours and hours and hours in libraries. And I could find nothing. And then I went back to my home in India. I was very dejected trying to write my book. And someone said, why don't you go visit a historian who lived a few blocks down from my house? And so one evening I took a stroll. I went to visit this historian, and this historian, as I finished my afternoon tea, he said, oh, by the way, I was in the Dana-Farber Institute with Sidney Farber in 1950. I said, really? Remember, this is Delhi, not Boston. And he said, oh, and I kept a whole file of all his patients. I said, really? And he said, oh, yeah, if you look on the top shelf, and I was coughing because it was so dusty, you'll find a file. And sure enough, in that file was a picture of this child. And that child is Robert Sandler. He's patient 0, the first patient to receive chemotherapy for acute lymphoblastic leukemia. He didn't live long, but he had a remission. And that remission was the first remission that's spurred the idea that you could use chemicals and biologicals to treat cancer. Now, you'll notice that this is not one picture. There's one child, but there's a second child here. I didn't know that. It turns out that this child had a twin, an identical twin. That has so many consequences for the biology of cancer. I'm not going to spend a lot of time on that. But years later, when my book got finished, I got a phone call in my office from someone I didn't know. And this is Elliot Sandler today. He had walked into a bookstore. He lives in Maine. He'd walked into a bookstore and found a book. Think about this for a second. Found a book dedicated to his own twin. And somehow or the other found a way to contact me and told me the entire story. My story was incomplete without him. And that's how I got to know the entire story. That's the story in the book of Robert and Elliot Sandler. And this is a picture from Ken Burns' movie about my book. And that's a picture of Elliot Sandler. And we still communicate once in a while. And he reminds me that it's very important to write histories, because these histories become stories, and these stories inspire generations. One of the most beautiful things, my book got lots of reviews, I would say mostly positive. And I don't care about those reviews that much. But the most beautiful review that I ever got for my book was Elliot Sandler's mother, Helen Sandler, the mother of these twins, had begged Sidney Farber of the Dana-Farber Cancer Institute to not perform an autopsy on the child. She had said that it's a desecration of his life. I just don't want this final desecration. I want this child to be whole. And Sidney Farber had begged her and said, please, it's the only way science learns is if we perform an autopsy, if we understand what went right and what went wrong. And she finally relented and she agreed to the autopsy. And the most beautiful review of my book was a small letter, 3 lines of email from Helen Sandler, who said that I finally feel relieved that that autopsy was performed because I felt that I contributed to science. Most beautiful thing that I've ever heard in my life. We fast forward many years forward, we go back to the idea of transformation. So, what is transformation? This is the work done by Harold Varmus, Mark Bishop, Bert Vogelstein, lots of people, who figured out the big problem of how a normal cell becomes a cancer cell. And to just remind you, there were 4 competing theories. The first theory was that it was heredity. And a Brazilian scientist, this shows you the international quality of this collaboration. And this is why, of course, NFCR is important, especially in its international reach. This is Hilario de Juvia, who argued that heredity was important because he had a form of eye cancer, we now know caused by a gene called retinoblastoma, across generations. So Hilario de Juvia said it must be genetics. Long before de Juvia, there was an English surgeon named Percival Pott who saw that chimney sweeps, young chimney sweeps, had a high incidence of cancer, and he traced it down to their exposure to chimney soot. And Percival Pott said that it must be the environment. It couldn't be, had to be the most obvious answer. We knew that there was chance because there were families in which there was no cancer. All of a sudden, there would be a woman or man with cancer. And an American scientist named Peyton Rouse won the Nobel Prize for showing that viruses could cause cancer. So how could we resolve this, what I call the 4 men in the elephant problem? There are 4 different, completely different theories: viruses, heredity, environment, and chance. And the answer lay, again, in this, which is to say that genetics was the center of all of this. That ultimately, whether it was viruses, heredity, environment, or chance, all 4 of these altered the genes in cells. These genes control cell division. These genes control other qualities that ultimately lead to cell division. And the capacity for a cell to become abnormally dividing is ultimately what causes cancer. So that was, I would say, the first crack at the theory. We'll go deeper into this shortly. But what were genes? The first thought was there was 1 gene, then there were 2 genes, there were 5 genes, there were 10 genes, etc. And then the Human Genome Project came along, and then the Cancer Genome Project came along. People often say, well, what's the use of the Human Genome Project? And I say, the most useful thing the Human Genome Project has produced is the Cancer Genome Project. So what has the Cancer Genome Project done? This is a picture of very schematically of a patient whose whole genome has been printed on a sheet of paper. Her first gene is here, it becomes like a snake, goes up and down, up and down, up and down. Her last gene is here. And let's say there are 20,000, 21,000 odd genes, plus, of course, all the intergenic spaces, so about 3 billion base pairs in all. And she happens to have breast cancer, and in her case, there are 1, 2, 3, 4, 5, 6, 7, 8 genes that are mutated. Another patient with breast cancer comes in, and Denny, I'm getting to you now soon. And she has a different set of genes, some common and some different. Her breast cancer looks exactly the same. Some genes are the same, some genes are different. Some genes are inherited, some genes are mutated by chance. We're still trying to figure out which ones are which. Here's a third patient with breast cancer. And again, you see the same pattern, some commonalities and some differences. And therefore, you can draw a map with big peaks and small peaks. The big peaks here represent very commonly mutated genes, the ones that I showed you were common. The small peaks represent the more uncommon ones. The really short peaks represent completely unique fingerprints of a breast cancer that are not present in any other person but in one individual only. And this is what the landscape of cancer looks like. And people have a very hard time understanding this idea. Again, I said before, cancer is something that is unique to individuals and yet is common between individuals. And here is that same idea now scientifically depicted in a map. Of course, we can find mechanisms by which we can attack the cancer. But what's really interesting and what's emerged right now is that these genes are not genes in isolation. They're not sitting there as big peaks. But in fact, they communicate with each other like a network. And I often liken this to a machine in which the purpose of this is a cell. The purpose of this machine is to ultimately perform multiple functions. It has to live, it has to metabolize, it has to respire, but it also has to divide in case it is a dividing cell. And each of these modules is not one gene, but is a collection of genes, a network of genes. And in many cases, there might be a hub, maybe here, maybe here, maybe here, maybe here, where a gene is mutated and is driving one part of the machine incorrectly. And as a result of that, the entire machine begins to malfunction. I call this the malignant network theory of cancer. It's not one single gene that's mutated, but a network of genes that's mutated. And therefore, sometimes attacking a single gene is successful, but sometimes attacking the entire malignant network may be necessary. And now we come to some successes. So this is the story, and I purposely put this in, of Herceptin. Herceptin is one such gene that sits right at the center of one such malignant network. It drives the growth of breast cancer cells where that gene is mutated, amplified. And it was Denny Slayman who recognized that that was the case. He identified it, not the only person, but he was the leader in the field. And Denny, you might recognize this patient. This is Barbara Bradfield. This is a picture that I took, by the way. This woman is maybe, could this be true, the longest survivor of breast cancer, diffusely metastatic, HER2-positive breast cancer. And this is her holding up her, you may like this picture, holding up her first dose of Herceptin. She had, if I remember correctly, 17 diffuse metastases in her lung, and she had given up her life, and she was almost convinced that she would never enroll in another trial. She was going to go to Mexico and drink juices. But Denny called her not once, but twice, maybe 3 times, convinced her to be in the trial. And here she is, still alive, the last time this picture was taken, and still flourishing from her treatment with Herceptin. What an incredible idea. Denny, stand up, please. And in the wake of Denny, any of you who work in breast cancer, please stand up and be recognized. Dr. Olapare, I can't see everyone, so thank you. This is the first trial of women with metastatic breast cancer, with and without Herceptin. These are so-called Kaplan-Meier curves, curves of death. As you die, you fall off the curve. Obviously, with no Herceptin, you die off much faster. With Herceptin, you die off much slower. This proved the idea that Herceptin was a powerful medicine that could stop the growth and the death of patients with breast cancer. But then something more interesting happened, and this is in my second and third book, which is that we began to combine Herceptin with early detection. So we said, why not take patients, and by we I mean the whole community of oncologists, said why not take Herceptin in the setting when patients are already diffusely colonized with breast cancer. But why not take patients who are HER2 positive, Herceptin, HER2, which is a target gene positive, and ask the question, what if we gave these patients early treatment? So this is Herceptin. This is a pivotal trial published in the New England Journal of Medicine. On the left side, you see, again, these Kaplan-Meier curves of patients with Herceptin, trastuzumab. And obviously, you can see that there's a big difference between patients treated versus not treated. This was known. This was reestablished. Wonderful news. Here's more important news in some ways. These are patients who have just been detected having lesions that are HER2 positive and given Herceptin after their tumors have been removed. They have no visible signs of a tumor. But they're still treated with Herceptin because of the possibility that their tumor has spread outside the breast. And they're given Herceptin along with other therapies now. And the difference between this is that the number 90% is important. And 5 years. Get this straight. 90% of women with HER2 positive early detected breast cancer that has been surgically and radiologically managed, given Herceptin therapy, are alive and flourishing, not alive and dying, but alive and flourishing at 5 years and now at 10 years. And I liken this result, I liken this to the cure of acute lymphoblastic leukemia. I liken this to the advent of antibiotics. This is a result as significant in the history of human therapy as any in medicine. And so thank you for bringing this, the entire community, obviously Denny included. All right, so I'm sorry the slide doesn't read very well, but I'm just going to read it quickly. But what I'm trying to say is that we're getting to a paradigm in which if we could detect early, in this case with Herceptin, in this case with HER2 positive breast cancer, if we could personalize and if we could do targeted therapy, that we would achieve a new kind of paradigm of cancer therapy. And all three of these are important. This is a triangle that we're trying to achieve. And so another way to think about this, going back to my first quote about how we think about this socially, culturally, phenomenologically, is to think about cancer as a disease of mitigated risk. How do we reduce those at risk? How do we identify those at risk? How do we detect early? How do we detect those likely to progress? how do we how do we treat with the most effective, least toxic therapy, and how do we maintain response and remission. And each of these I try to divide into three categories, because three groups of science, people think differently, and three very accomplished groups of scientists are moving in all three directions. So how do we detect those at risk? Of course, there's an old way. We used to ask questions about history, exposure, and heredity. Now we go from, this is a breast cancer, it's a family with breast cancer, and we now go to genetics more and more. So this is the new genetics of breast cancer. It's no longer restricted to just BRCA1 and BRCA2. We detect early by asking a very deep question about exposure, about history, but most importantly about genetics. These are patients who are BRCA1 and BRCA2 negative, but have a history of breast cancer in their family. They were called BRCA3 in quotes because there was not one gene. It turns out there are dozens of genes, and we can now find them. If you have a history of breast cancer in your family, go see a genetic counselor, because the genetic counselor may be able to advise you about whether your history is genetic, and if that history is genetic, may be able to tell you how, just ignore the details of the slide, but about how to manage your risk in the future. So the question is, how do we detect early? We detect early through a detailed history of exposure, a detailed history of risk, and most importantly, a detailed genetic history, some of which can be done by gene sequencing. How do we detect early in other diseases? I'm not only talking about breast cancer. This is a friend of mine who unfortunately died of melanoma, Will Kiersky. In his case, we were able to detect his primary lesion using AI. So this is an AI module published by Stanford University, in which 500,000, not the number, 500,000 lesions were classified as benign versus malignant based on characteristics that we don't understand, but based on characteristics that an algorithm understands. And amazingly enough, this performs better than any dermatologist. And it is an incredible testament to what we're going, that we can now detect early, not only using genetics, but using biology, using AI, and other mechanisms. Next question is, who's likely to progress? How do we know who's likely to move forward? If you happen to work on the transition, I do, between pre-cancer to cancer, DCIS to breast cancer, MDS to leukemia, please stand up. I know you're there somewhere, Nelly. Thank you. So who progresses, and how do we stop that progression? What are the markers of progression? How do we understand that? Again, extremely important, because if we could halt that progression, we could change the way people progress. And finally, how do we treat with the most effective, least toxic therapy, and how do we maintain responses and remissions? So I'll end with my own work, but I'll call out people as we finish this work. The first thing I'd like to say is, we talk about immunotherapy, lung cancer, and melanoma. Everyone knows this. This is now a classic story. Immunotherapy has revolutionized cancer therapy. We now recognize that it's not just the tumor, it's not the genetics of the tumor, but things that happen outside the tumor that are important. And of course, this is the pivotal trial for melanoma, which recognized that the immune system is one of the mechanisms, not the only, but one of the mechanisms by which cancer can be controlled. This is the case of melanoma. We know that this is the case of lung cancer as well, and now more and more cancers. I'll finish up with I talk about three themes. I'll talk about three themes in my own work. Most recently, I have a strange new thing going on in my life is that I've launched a project with Microsoft and AI to test in silico, and by that I mean in a computer, per single target, 10 billion drugs that have been created by the computer. People often say they forget the word 10 billion. 10 billion is a very large number. It takes us 1 week, if we have a good target, to test 10 billion drugs. It would take dozens of years to test 10 billion drugs. We don't know if these can be synthesized. We don't know if they can be made, but there's still 10 billion. This is the pipeline. You don't have to care about the pipeline, but you have to care about this. In gray is the target protein. It doesn't matter. This happens to be one target protein. In blue and yellow and white are candidate chemicals out of 10 billion. This is a sampling, which have been docked onto the active site of that molecule. And we know the exact energetics. We know the synthesis pathway for all 10 billion of them. And they're moving around because our chemists want to look to see if they're real or not. So once they come out of that pipeline, and every campaign tests about 10 billion. And we can do these for small molecules, and we can do this for antibodies like Herceptin. We can do this for a variety of small molecule combinations. So what we're going to see in the next dozen years is that the FDA is going to be very, very, very busy, which is a good thing. I trained one of the folks who works at the FDA, Yusha. I don't think I taught you anything. I just taught you to be busy. So, Yusha, you're going to be very busy because we are generating on a weekly basis tens of thousands of candidates. Now, the work doesn't end there. We have to go into animal models. We have to do a preclinical package. This is, I would say, in silico work. It's not fictional, but still it's early work. But again, every time we launch 10 billion chemicals. This is a second trial that I'm involved in. This is a fascinating trial in which we combine, and we can talk about it later, we combine gene therapy with, with immunological therapy for acute myelogenous leukemia. AML used to be the most lethal, or one of the most lethal of all cancers. People talk about pancreatic cancer. AML is one of the most lethal of all cancers. With the help of Raju, stand up. I created a new way of treating AML completely outside what is known. We use CRISPR to delete a gene so that the cells of a person become immune to a toxic therapy and only the cancer cells remain sensitive. And this trial, the first patients are now out 2 years or 2.5 years. And it is widely recognized as the single most successful therapy against AML in trial today. All right, I'll give you a third one. And this concerns economics. I started a company in India, despite everyone telling me not to do so, called Immunil Biopharma, to make CAR T therapy accessible for patients with ALL, acute lymphoblastic leukemia, those very same children, Robert Sandler, Elliot Sandler. The cost of CAR T therapy in the United States, all in, including hospitalization, was about $600,000. I argued that it should be 1/10 of that and possibly 1/20th of that. So we now are we created a fully integrated GMP facility in 1 year. By the way, during COVID, this was made during COVID. And we are now offering this at about 1/10 the cost, moving towards 1/20th the cost. This is patient 0. I took the mask off him because he is now publicly known. This is patient 0, alive today with relapsed ALL. And we have about 30 patients, 1/10 the cost, and 80% patients cured of ALL. So very soon, we're hoping that you wouldn't go. By the way, our list of patients, we have about a population of about 1.2 billion people. Our list of patients with ALL is about 10 times the number of patients that we can possibly treat. We're treating patients from North Africa. We're treating patients from the Gulf region. We're opening a center in Saudi Arabia, opening a center in Dubai, because I'm afraid to say, although the United States has remained the center for scientific innovation, it is no longer the center for clinical innovation. And unless organizations like NFCR exist and step up, we will lose our capacity to become the center for clinical innovation. And that will be an incredibly sad thing. We should lament that so deeply, because if we do not remain the center for clinical innovation, we will have lost our position in the world as the central disseminator of clinical information. I'm really sorry to say that. We recruited this trial in 12 months. I tell people it would have taken 30 years for us to do this trial in the United States. Now, to finish up, there are people who often complain that, the emperor of maladies came to a stop somewhere, and that's because that's what we knew then. I'm writing a new edition, which will have 3 or 4 more chapters, which will add to the new things. Immunotherapy wasn't there. Our understanding of the role of the microenvironment wasn't there. The organism, the host, the tissue, microbiome, immune system, things that I call outside the tumor. People call them microenvironment and other things. And I'll end with this, which is, look, this is a famous New Yorker cover about how people think about New York. They think about New York as 9th Avenue, 10th Avenue, and the rest of the world in faraway places. We have to change that thinking. There's cancer. There was a genome. This was where we were in the 1990s and early 2000s, and it has brought us incredible therapies. But there's a world outside. There are cells. There's the microenvironment. There's patient-host, microbiome, metabolism, going back to Albert Szent-Györgyi. And so a more holistic way, but not a fuzzy way, but a more holistic way of thinking about cancer is to incorporate all of this and to understand all of this as we move forward in the future. And there's a great new mechanism by which we can understand all of this. So as my final point of recognition, if you happen to work not on the cancer genome, but on the cells, the microenvironment, metabolism, patient host, and the microbiome, stand up, because you will be likely the scientists of the future, because that's where our world is going. And with that, I would like to end again by re-quoting Stephen Shapin. A world in which cancer is normalized as a manageable chronic condition would be a great thing. It might decrease the incidence of some forms of malignancy while hugely increasing the number of healthy people under medical treatment. It would be a strange victory in which the price to be paid for checking the spread of cancer through the body is its uncontrolled spread through our culture. And our job as physicians, as stewards of the medical space, is to prevent exactly that, is to find a world in which we can simultaneously prevent cancer, treat cancer, but not allow it to spread in a malignant way through our societies and cultures such that it becomes the preoccupation of our lives, but rather becomes something that we think about when we think about ourselves as ill, but we also think about ourselves as creative individuals that can conquer something that is so important to society and to our cultures. Thank you very much, and congratulations to NFCR.